All right, so sorry to keep you in suspense. How about this problem here? We started with this integral from -1 to 1 of x squared dx, and we said, wait, FTC does not apply. How come? Do you see it? Yeah, the problem is that 1 over x squared looks like this. From -1 to 1. And so 1 over x squared is not continuous. And so therefore the fundamental theorem of calculus does not apply for this. Good. There is a technique to see if there is a way of getting around this problem, but we're not going to be looking at that this semester. You'll see that next semester in Calc 2. Okay, so I think what we'll do is just work through a few example problems from the homework, or at least from this from the book, and see how it goes. Okay, I'll pause here and write down the first couple of problems. Okay, so let's try a few derivatives. So this is number 8 from section 5.2. Go ahead and erase the little graph from the last one. Give it some space. So if I want to take the derivative of this function, this looks like it's all lined up for us from the fundamental theorem, right? Which said that the derivative of this function, if this is g of x, then g prime of x is just f of x. Oops, I didn't leave myself enough space. So in this case, we're just plugging things in. So in this case, we just have e to the x squared minus x. Good. And notice that this has to be in x, right? While this was in t. In fact, well, we'll get around to that later. How about the next one? Let me not call that little g. Let me call that big G, just in case. We're going to use little g later on. So how about this? Uh-oh. There's a problem here, isn't there? X to pi, but I'm noticing in my original expression up here, right, from the fundamental theorem, that I need a in the bottom and x on the top. So the variable needs to be at the top for the fundamental theorem to work. And so is there a way I can rewrite g of x so that I can get it in the right form? Why, yes. That's the same thing as minus the integral from pi to x sine of t squared dt. That's one of the properties of a definite integral. Good. And now when we differentiate, g prime of x now will be just the sine of x squared. Good. And now how about this one? The last one here. H of x is equal to 1 to the square root of x z squared dz. That's weird. Because up here I have x, I don't have a function of x. However, if we let g of x be defined to be the integral from 1 to x z squared dz, then the integral from 1 to the square root of x z squared dz is a composition of g with the square root of x, right? Right, so if g of x is defined this way, then to compute g of the square root of x, you plug in square root of x wherever you saw an x before, right? And so this is now, so this is a composition. Good. And so you could rewrite then h of x is equal to g of the square root of x. And so h prime of x is equal to g prime of the square root of x. But now you have to multiply times the derivative of the square root. Right? And now what is g prime of the square root of x? Well, coming back here, if g of x is equal to that expression, g prime of x is just going to be x squared, right? But we're not putting in x squared, we're putting in the square root. So we evaluate, oops, let me, yes. Yeah, the notation's getting a little funky here. x is being replaced by the square root of x. Oh, that looks so bad. Sorry about the notation. Okay, so we got to rewrite that. Yeah, in place of the x up here, I'm putting in the square root of x. So that's going to be the square. I'll go ahead and write it this way: square root of x squared, and then times our derivative that we're just bringing over. Okay, and so that ends up being, if x is positive, and it should be, then that's just going to be x over 2 square roots of x. Does that simplify? 1 over 1/2 square root of x. Good. All right. And so let's review that. If we have the integral from a to, let's say, h of x, f of t dt, how do we differentiate that? Then d over dx we can think of as a composition, so it's the derivative of g of h of x, right? And so the derivative is going to be g prime of h of x times h prime of x. And so let's put it back into this notation. G prime of x is f of x, so that's going to be f of h of x times h prime of x. Good. So if you have a function up here instead of just the variable x, then we have to be a little bit more tricky there. Let's try one more. Let's try the most general form. Suppose that you have the integral from h1 of x to h2 of x, f of t dt. Is there a way you could rewrite this integral like we did up here to make this make sense? Well, you could rewrite this as, let's take this from from the bottom first, I guess. h1 of x to a, f of t dt, plus the integral from a to h2 of x, ft of x, or f of t dt. Good. And then we know, so this is just a property of the integral, right? You can break it apart with that value a there. And so furthermore, what we learned is you could also flip the bounds on this. So this is going to be minus h1 of, minus from a to h1 f of t dt, plus the integral from a to h2 of f of t dt. And now both of these are set up for derivative. So if I differentiate, the derivative is going to be minus f of h1 of x times h1 prime of x plus f of h2 of x times h2 prime of x. Normally we would write these in a different order. We would say that the derivative of h1 of x to h2 of x, f of t dt, is equal to the f of h2 times h2 prime, so that's a composition, right? Minus f of h1 times h1 prime. Good. And so that is the most general form of our derivative. Good. So just as a quick example, gosh, doesn't our book have any examples? How about take the derivative of the integral from 1 plus 2x to x squared of the sine of t dt. I'm not being very random today. Okay, so that's going to be the sine, but now I put in my h2, the top function, which is x squared. I multiply by that, 2x minus the sine, and inside there I put in my 1 plus 2x, multiply by its derivative, 2. Good, that's it. Okay. So, do we have time for one more? I think maybe we'll just make one more video with a few more examples. Okay, we'll see you then.